Welcome back to Math 332. This is the third review video for the exam, and in this video we are going to talk about the relationship between the rank of a matrix and the nullity of the matrix and how we use that to solve several problems in your practice exam. Now before we do that, a quick review. So suppose you have a matrix A, the same matrix as the one that we saw in our second video, and we are considering the system AX equal to B. Now, because of the size of the matrix, we can see that the X here has to be 5 by 1 and the B here has to be 4 by 1. Now, by now you also know that when you multiply this matrix on the left, what you do is basically taking the X1 and then multiply the first column of your matrix A, and then plus X2, multiply the second column of your matrix A, so on and so forth. So whether or not the system is has a solution, which means that it is consistent, or whether or not the system is does not have a solution, which means it is inconsistent, that would depend entirely on whether or not these vectors b1, b2, b3, b4 can be written as a linear combination of these column vectors. Another way of putting it is to say whether or not this vector b is in the span of these column vectors, and we already know that the span of these column vectors are known as the column space of A. So one last time, let me say that again, this system is consistent or not will depend entirely on whether or not this vector b is in the column space of A. Okay, so recall that the dimensions of the column space of A is also known as rank of the matrix is 3, and the column space of A is actually a subspace of R4 because R4 have 4 dimensions. This one here has only 3, so we know they are not the same set, which means that there must be some kind of B in R4 that is not in the column space, and if it's not in the column space, this system will be inconsistent, right? So instead of speaking in abstractions, let me show you one example. So this B here, 0, 0, 1, is actually not in the column space of your matrix A, and therefore the system is inconsistent. We can verify that pretty easily by putting 0, 0, 1 into the augmented matrix like that, and then row reduce it. And then you will see that the last row here is, this part here is entirely 0, but this is 1. So we know that the system is inconsistent. Okay, so this tells us that if the rank of a matrix, in our case, our B is in R4 and your rank is less than 4, then that is a possibility that you can find B which can make the system inconsistent. It's not that it is a possibility, it's definitely the case, okay, that you can find some vectors that the system is inconsistent, okay? Right, so another thing that we can deduce from the rank and the nullity of a matrix is suppose that now the system is consistent. Let's just assume that. The next question we can ask is whether or not the system has a unique solution or it has infinitely many solutions. Well, that will completely depends on the nullity of a matrix or the null space of a matrix. Now we talked about this in class before. The AX equals to B, if it is consistent, then the solution, the general solution of the system is going to look something like this. X naught here is what we call a particular solution, which is the one that gives AX naught equals to B. And then this part here is coming from the null space, all right? From the null space of the matrix A. So we can see that this obviously will give AX equal to B, because if you multiply A here, so AX here will be the B, and then you multiply A here because this is in the null space, so A of this vector is 0, A of that vector is 0, so A of X is AX naught, which is B. Okay, and also from these general solutions, you can see that the system has unique or infinitely many solutions, will depend on whether the null space is actually just consists of the 0 vector or it consists of non-zero vectors like the one that we have here. So if it consists of non-zero vectors, so just changing the k1 and k2, you can generate infinitely many solutions. If the null space is only 0, so no matter how many times you multiply the 0, it's just going to be 0, and you have only one solution, which is the X naught. Okay, so if the questions ask you whether or not a system has infinitely many solutions or have unique solutions, you will always have to refer to the null space of A. Okay, and another things that I want to mention, just in case you forgot. So if a vector space we know that vector space cannot be an empty set. We know that 0 definitely is going to be in the vector space. So if the vector space only consists of a 0 vector, then we say that the dimensions of that vector space is 0. This is a vectors and this is a number. So apply to the null space. So if the null space consists of only 0 vectors, then the nullity of the matrix A is going to be 0. Okay, all right. So so just remember that if the questions ask you for whether or not the system has infinitely many solutions or have unique solutions, you will always have to refer to the null space, okay, of that matrix, and or the nullity of that matrix. Now, another thing we want to mention is this particular observations. So suppose you have a matrix A of size n by n. We're going to see that in a moment that the rank of that matrix will be at most the minimum of these two values, okay? All right, it happens to be less than or equals to the minimum of these two values, the row and the number of rows and the number of columns. So I'm going to use this example to illustrate this fact. So suppose you have a matrix A of size 3 by 2, 3 rows and 2 columns. And try to imagine that we row reduce it all the way to RREF. If you remember from our second video, the way to determine the rank of a matrix is always by referring to the RREF of a matrix. It's the same thing also in order to determine the nullity of the null space of a matrix. You also always refer it to the RREF of a matrix. So if you are given a matrix A of size 3 by 2, you look at the possibility what type of RREF of matrix A will looks like. So one possibility that it will look like this: you have a pivot here, you have a pivot here. So you can have a maximum of 2 pivot, right? Because if I ask you to put another 1, you cannot put it here. That will not be RREF. You cannot put it here also. So for a 3 by 2 matrix, the maximum number of pivots that you can have is 2, and we know from the last video the number of pivots corresponds to the rank of a matrix. So you can have rank 2 matrix, okay? And if you are rank 2, then the nullity and the rank relationship says that if this is 2, and this always have to add up to the number of columns, which is in our case 2. So if this is 2, so this has to be 0 in order to be 2. So the nullity of this matrix will be A, which means that if this system AX equal to, let's say, B, if it is consistent, then it will have to have a unique solution because the nullity is 0. Now, the another possibility of the RREF of A is going to be only have 1 pivot. So in this case, the rank is 1, and the nullity will be 1 because the sum of these two has to equals to the columns, which is 2. And there's also a possibility that a matrix A is just a 0 matrix. So if your matrix A is just a 0 matrix, then the row reduce it to REF form will be also a 0 matrix. In this case, because of the column are all 0, so the linear combination of the column vectors is 0. So the rows, the rank, the column space, or even the row space, they all just consist of the 0 vectors. So therefore, the dimensions is 0. And because of the rank and nullity informations, we know that the nullity has to be 2. So we can tell that also from these observations that the rank of the matrix has to be the minimum of that 2. It cannot have, if you have only 2 columns, that's just 2. You can only place maximum 2 pivots here. So the rank always has to be maximum 2. It cannot be more than 2. And so we see that this relationship hold in this case. And actually, if you just give it a little bit thought, you can see that in general, this must be true. Okay, in general, this must be true. Okay, so this gives us tools to answer some of the question here. Say, for example, if you have a matrix A size 4 by 5, the question is whether or not this system of equation must have a solution. Well, we know that this system has a solution or not, well, depending whether this matrix, this vector B is in the column space of A, it is not in the column space of A, right? Okay, so let's look at the second questions before we look at the solutions. So the second question says that if your matrix A is 4 by 5, if this system has solutions, must the solution be unique? Can we have more than one solutions and stuff like that? So let's use the tools that we have developed to answer this question. So the first questions I can't answer that already. So the answer to the first one, whether or not the system is consistent, will completely determined by whether this vector B is in the column space or it is not in the column space. Now, so suppose it is in the column space. So it can go both ways. It could be consistent, it could be inconsistent. The rank will not tell you anything about it. You will really have to see whether or not B is in the column space of A or it is not in the column space of A. The second question is assuming that it is in the column space of A, therefore the system has a solution. So the question is whether they have infinitely many solutions or it have only one solution. So rank of A must be at most, okay, the minimum of these two numbers, which is 4. So the maximum rank is 4. So if the maximum rank is 4 and they have to add up to 5, if the maximum rank is 4 and you have to add up to 5, which means the nullity of A cannot be 0. It has to be at least 1. So the nullity of A cannot be 0. It has to be at least 1. That means that the null space is not consist of only the 0 vectors. So if you look at the solutions will be like some particular solutions, and then you have some non-trivial null space. So this is the place that will generate infinitely many solutions. So because of that, we know that AX equal to B, if it exists, the solution exists, it cannot be unique because the null space is not 0. Okay, another questions that we can answer is that if you have a matrix 5 by 5, it's a square matrix. If it is invertible, what is the rank of this matrix? So the rank, if you are 5 by 5 matrix and this matrix is invertible, what is the rank? And I'm claiming that the rank has to be 5. This is what we call full rank. The reason is pretty simple. Okay, the rank must be 5. The reason is pretty simple because if the matrix is invertible, this matrix A is invertible. If the matrix A is invertible, then we have only one solution. The solutions for this X is going to be A inverse B, all right? So you have only one solution. The system is definitely has a unique solution if A is invertible. That means the null space is a 0 vector. So the nullity of A is 0. So again, apply this rank and nullity equations. So this has to be 0. This means that it has to be rank 5. Okay, so these are just some of the example on how we can apply this relationships between the rank and the nullity of the matrix in order to answer several different type of questions, especially those questions in the first sections of your practice exam. Okay, and this will be the end of all the review videos, and good luck for your exam.